I welcome you all to this session on thermodynamics. Today we are going to the module 2, work and heat. The topics which we are going to cover in this class is definition of work, definition of heat, sign convention, then comparison of work and heat. Now, while defining thermodynamics itself, we said that major application of thermodynamics comes in where we are interested in converting heat into work. So, in this module, we are going to learn the different equations for work as well as heat and the ideal processes which are there in displacement work or other types of works as well. Now, look at the mechanics definition of work. We already have come across with the definition of work in mechanics. That is, work is said to be done when the point of application of force moves an object in the direction of force. That is, you call it as work in mechanics. That is given by the formula force into displacement. Correct. Work in mechanics is the product of force and displacement. So, you call it as work only when there is a displacement. If there is no displacement, there is no work in terms of mechanics. But thermodynamics definition of work is a bit different, but let us describe the thermodynamics definition of work with a simple example. How it is different from that of mechanics of definition of work, we will see. Now, let us consider a system of battery. This boundary, the dotted line is indicating the system boundary, and this is the system which we are considering, that is the battery. Then we have a system like a switch and a resistor. Then everything external to the system we called it as surrounding. If you close the switch, what will happen? The resistor gets heated up by consuming the energy from the battery. But according to mechanics definition of work, there is no displacement. So, this cannot be called as work in mechanics because there is no displacement except you neglect the work which is there in switch, okay, displacement which is there in switch. So, the resistor gets heated up, but according to mechanics definition of work, there is no work because there is no displacement. However, if you consider the same system, a battery, and that instead of a resistor, I am going to replace the resistor with a motor. Then, if I close the switch, what will happen? There is an attachment of pulley and there is a weight. You can have the displacement of the weight, or you can raise the weight by the same system of battery. In this case, you consider this as a mechanics, you consider this as a work in mechanics because there is a displacement. However, we can see that this system can be converted to this in order to define or in order to have the work in mechanics. So, what we will do in thermodynamics definition, if one need not to change the system to a motor kind of a system. If you can imagine a battery system, then if you can imagine that there is a possibility of lifting a weight, rising a weight, then that itself can be called as a work in thermodynamics. That means one can imagine that if I replace the resistor by a motor, this can be called as thermodynamic work. That is what we are defining. Work is said to be done by the system on the surrounding if the sole effect external to the system is said to be rising of weight. So, one need not to make the change. If one can imagine that if this system can be replaced by a motor, then it can be reduced to rising of a weight, then they all come under the work, that is thermodynamics definition of work. So, even this system is considered to be doing work, that is we call it as electrical work. We have other types of work, surface tension work, we have electrical work, we have displacement work, we have magnetic work. All the other types of work comes under this type of category, whereas displacement work is nothing but the mechanics definition of work only. So that is about the difference between mechanics definition of work and thermodynamic definition of work. Now unit of work is joule. Joule is the name of the scientist. So however, joule is equal to 1 joule is equal to 1 Newton meter. It is like if you have a weight of 1 Newton, if that can be moved by a distance of 1 meter, then you call that as 1 joule. That is what is the meaning of 1 Newton meter. Now we will go on to study the definition of heat. What is heat? Heat is a transfer of energy. It is also the form of energy. The earlier definition of heat is a bit different. People thought that heat is an invisible fluid which flows from one body to the other body. Okay, but today we know that heat is a form of energy. It is a transfer of energy by temperature difference. Heat is defined as a form of energy which transfers only by the virtue of temperature difference. If that is happening, you call it as heat. You cannot say that heat is stored in a body. Okay, the body may be having higher temperature, you say, the body will have lesser temperature. Heat transfers from higher temperature body to the lower temperature body. The unit of heat is joule. Of course, the earlier unit of heat was calorie, then we had to have a unit of conversion, but there is no confusion. The unit of heat is joule, and once again that is also given by 1 Newton meter. Now we will look at the difference between heat and work. Work is energy interaction other than temperature difference. So all the energy interaction other than temperature difference, we are calling it as work in thermodynamics, whereas heat is the energy interaction only when there is temperature difference. So if the energy transfer is happening because of the temperature difference, that is heat. Now any energy transfer other than temperature difference, they are work. Now work is a high grade energy. When do you call it as a high grade energy? When you can transfer one form of energy into other forms of energy more effectively, then that is called as high grade energy. Work can be transferred to any other forms of energy with 100% efficiency, at least theoretically, whereas heat is called as low grade energy because heat cannot be transferred to other forms of energy completely, like with 100% efficiency, where you need a heat rejection, which we will discuss in second law of thermodynamics later. But know that work can be converted into heat 100%. For example, if you consider a rotating drum, and if you are trying to apply the brake, all of the work which was there, all of the kinetic energy which was there, can be completely converted into heat energy, 100% at least theoretically. Whereas when it comes to heat, you cannot have a 100% energy efficiency in conversion. You cannot convert heat into work with 100% efficiency. That's why we always call heat as a low grade energy. Now this is the sign convention. Work, if it is done by the system on the surroundings, it is considered to be positive, whereas heat added to the system is considered to be positive. Okay. Then work, if it is done on the system, it is considered to be negative, whereas heat rejected by the system to the surroundings, it is considered to be negative. We will look at the similarities of work and heat. That is, both are path function and inexact differential. Both this work as well as heat are path functions. They depend on the path, not the point. That is like they are boundary phenomenon. Both are boundary phenomenon. You said while we defining work and heat itself, we said that a system cannot possess heat or work. They are identified when the energy crosses the system boundary. You cannot say that the system has this much of work or system has this much of heat. It is always identified at the boundary. Okay. Both represent transient phenomena. Then a system may possess energy but not work or heat. We will look at displacement work or PDV work for ideal processes. But before looking at the ideal process, we will see what is PDV work. While defining work, we said that there are in thermodynamics work is a bit different from that of mechanics of work. But however, thermodynamic work all considers mechanics of work also. So this is nothing but displacement work is nothing but whenever there is a displacement. So you call it as a displacement work. So work in mechanics can be defined as force into displacement, where force here pressure can be given by the formula force by area. So force will be pressure into area. Substitute force is equal to pressure into area here. Then work will be pressure into area multiplied by displacement. Then area multiplied by displacement can be called as change in volume. So work can be given by pressure into change in volume, that is P dV. Hence it is called as PDV work. Now PDV work or displacement work, we will do it for 5 ideal processes. Ideal processes are constant pressure process, constant volume process, then we have constant temperature process, polytropic process, and then reversible adiabatic process. Now first what we will discuss is constant pressure process, or it is also called as isobaric process, where pressure is constant. Now try to draw a PV diagram where y axis indicates pressure and x axis indicates volume. So constant pressure is constant means there has to be a change of state for it to be called as a process. Now there is a change of state but pressure is remaining constant. We have taken from this to point 1 to point 2 in this direction. It can be reverse also, like from 2 to 1 also you can plot, that also will be constant pressure. A horizontal line in a PV plot will be a constant pressure process, because the pressure changes vertically. Here it is a horizontal line, so it is called as constant pressure process, or it can be represented by a horizontal line in a PV diagram. How one can imagine a constant pressure process? Like if you have a balloon and if you are trying to blow it, what will happen? As soon as the pressure inside the balloon, if you try to blow it, then as soon as the pressure increases in the balloon, it tries to increase its volume against the atmospheric pressure. So it will not allow the pressure inside the balloon to increase. So in other words, it is like a constant pressure process. It is trying to keep the pressure inside the balloon a constant. So very similar to that, but the volume has changed. So it is quite similar to the process which we are talking, a constant pressure process. It will be from point 1 to point 2. Now how to derive the work for this? We will see. Constant pressure process. So we said it is an inexact differential. It depends on the path. You cannot say that the amount of work at point 1 or the amount of work at point 2. It is a path function. So work 1 to 2 or WO 1 to 2 we call it as. So inexact differential we said, so always it is like delta W we write it as, not dW, is equal to P dV, integrate it between the limits 1 and 2 because the process is happening between 1 and 2. Then what we have is pressure, we will take it outside the integration because pressure is constant. Then integration of 1 to 2 dV. Integration of dV is V, then integration limits 1 and 2. As we said, we are representing W or work 1 to 2. That is the work which is happening between the process 1 to 2. It can never be like work 1 or work 2. Because it is not a point function, it is a path function, work 1 to 2. It depends on the path. That's why we said inexact differential. But whereas the volume can have the values at the point. You can say that the volume at 2, V2, you can say volume at 2 can be whatever the value, 2 meter cube, 1 meter cube. Similarly, V1 we can say, P1 we can say, P2 we can say, but W1 we never, because it depends on the path or it is inexact differential. Now come back here, we apply the integration limits V2 minus V1. This is the formula we want for calculating work if the process is constant pressure or isobaric process. Now look at the unit, pressure is Newton per meter square, volume is substituted in meter cube, meter square and meter square get cancelled, so 1 meter is left there, that is Newton meter, which is called as joule. So obviously the unit what we are getting is in joule. But look at here, if that equation is giving me the work transfer between process 1 to process 2. Now if I reverse this process from 2 to 1, then work 2 to 1 will be P into V1 minus V2. What we are trying to say is that the equation, you should not mug it up, it should be like pressure into V final minus V initial. That is, here V final is V1 because the direction we have changed, V1 is the V final and V2 is the initial value, constant pressure. So pressure into V final minus V initial. We can change the process like 5 and 6, let it be the same direction. Now what will be the equation? Pressure is constant, let us say the process is from 6 to 5. The equation is pressure into V final, that is V5 here, minus V6. So this needs to be understood at the beginning itself, that the equation is pressure into V final minus V initial. Now if you look at the diagram for that equation, that is P into V2 minus V1, it is V2 is greater because we are trying to see whether this gives us the positive or negative answer. V2 is higher value whereas V1 is less, V2 is more and V1 is less. In that case V2 minus V1 will be positive. So whenever in a PV diagram, if the curve is from left to the right, you can say that it is a positive work because you get that this value as positive, so it will be positive. If you reverse the direction, what is the equation? P into V final, that is V2 minus V1, the same equation because final here is 2 and initial is 1 only. Now V2 is lesser than V1, V2 is lesser than V1, you get negative answer. So obviously one can see in PV diagram itself whether the work for the given process is positive or negative. Let us look at the second ideal process, constant volume process, or it is also called as isochoric process, where the volume is constant. In a PV plat, it is very simple. Volume is constant means volume should not change. So the x-axis indicates the change in volume. So there is no change in x-axis, so it is a vertical line. So it is a change in pressure, there is no change in volume. So the process is indicated in a PV diagram like a vertical line, that is from point 1 to point 2. If you indicate a vertical line in a PV diagram, it will be a constant volume process. It can be from 1 to 2 or in the reverse direction. In both the case, it is a vertical line. Now let us look at the work done equation for constant volume process. The same equation, the work is equal to PdV, integrate it between limits 1 and 2, but here since there is no change in volume, work transfer in constant volume process will be 0. Very important, if there is no change in volume, there is no question of work transfer. Next ideal process which we are looking is constant temperature process. We also call it as isothermal process or hyperbolic process, because the nature of the curve what we get is hyperbola. So temperature constant process. It can also be called as PV is equal to constant, because we know that as long as it is an ideal gas which we are talking, PV is equal to MRT, where mass will be constant in a closed system, then R will be a gas constant, then if the temperature is also constant, this whole term on the right side will be constant. So temperature constant or isothermal process can also be called as PV is equal to constant or T is equal to constant. Now we get this hyperbola in constant temperature process. Unlike in constant pressure we had a horizontal line, in constant volume we had a vertical line, but since we are not plotting in temperature graph, it can neither be horizontal or vertical. So for a pressure, in a pressure volume plot we are plotting, so obviously the temperature, if it is constant, that is how the combination of pressure and volume varies. That is what it is trying to show you. So the behavior of constant temperature are the points which you can locate for each state change. For a constant temperature will look something like this. That is the graph which we are trying to denote. Now it is also called as PV is equal to constant. Go for the same equation, delta W is equal to PdV, integrate between the limits 1 and 2, then what we have is PdV. You cannot take P outside because pressure is not constant. Then go for the equation which we know, that is what we said, PV is equal to constant. If PV is equal to constant, PV can be written as P1 V1 should be also equal to P2 V2. The product of PV at 1 will be same as that of the product of at 2 PV. So that is what we are trying to say, P1 V1 will be equal to P2 V2. But what we have is P. So we will take this part of the equation, PV is equal to P1 V1, solve it for P, what we get is P1 V1 by V. Then substitute it for the place of P, P1 V1 by V, then we can integrate it. Now P1 V1 is constant, take it out of the integration limits, then what we will have is 1 by V dV, where integration of 1 by V is ln V, put the integration limits 1 to 2, then P1 V1 ln V2 minus ln V1. Then work 1 to 2 will be equal to P1 V1 ln of V2 by V1, because ln A minus ln B is equal to ln A by B. Therefore, this equation is giving us the work transfer in a constant temperature process or isothermal process. The next ideal process which we are going to look at is reversible adiabatic or isentropic process. We are calling it as reversible because the process is reversible. Even though all the ideal process which we talked about, all are reversible, but we are specially mentioning it here because only when it is reversible it will be isentropic, that is entropy remains constant. It is too early to talk about the entropy. Just know that reversible adiabatic process means adiabatic. We had defined already what is adiabatic. In adiabatic there is no heat transfer which is taking place between the system and surroundings. So reversible adiabatic means a process which can be reversed. So reversible adiabatic process. In reversible adiabatic process, the PV power gamma value will be constant. That is like P1 V1 power gamma will be equal to P2 V2 power gamma. Now we are interested in deriving work transfer equation for the ideal process, that is reversible adiabatic process. Now the equation which we know for work transfer is delta V is equal to PdV. Now integrate it between the limits to get the work transfer. We know that P1 V1 power gamma is equal to P2 V2 power gamma, or it is also equal to PV power gamma. Now get the value of P here in terms of V, because here we have to integrate it with respect to dV. So P is equal to P1 V1 power gamma divided by V power gamma. Substitute this value in equation 1, that is value of P here, P1 V1 power gamma divided by V power gamma, and then we have dV here. Now take out P1 V1 power gamma outside because it is constant. As we said, PV power gamma is constant in this process. Then what you will have within the integration limit is 1 by V power gamma. Then in order to integrate, what we can do is take this to the numerator, V power minus gamma dV. Now we are ready to integrate. This side it will be W of 1 to 2, then P1 V1 power gamma, V power minus gamma. We know that integration of x power n is equal to x power n plus 1 divided by n plus 1. So V power minus gamma plus 1 divided by minus gamma plus 1, the integration limits is 1 to 2. Now divided by, you can write it as 1 minus gamma, then substitute the integration limits here, V2 1 minus gamma minus V1 1 minus gamma. Now simplify that equation. 1 to 2 is equal to, while multiplying with the first term, assume that as P2 V2 power gamma, because P1 V1 power gamma is equal to P2 V2 power gamma. While multiplying to this, keep it as P1 V1 power gamma only, because as we said, in order to simplify this, here it will be better if the term is P2 V2, whereas here it is better if the term is P1 V1. So that is what we are going to do. 1 by 1 minus gamma I will keep it outside, then multiply. While multiplying with the first term, I will keep this as P2 V2 power gamma, then this is always there 1 minus gamma. Then while multiplying to the second term, keep it as P1 V1 power gamma, then V1 power 1 minus gamma is there. So we have not changed the meaning of the equation. The term which we had, this term P1 V1 power gamma is equal to P2 V2 power gamma. Even if you substitute it P1 V1 power gamma, that is also same. Just for the sake of simplicity or simplifying this equation, we considered it as P2 V2 power gamma. Then simplify this, P2, then V2 power gamma, V2 power minus gamma cancels out. What you will remain with is V2. Then V1 power gamma and V1 power minus gamma cancels out. Then what you will remain with is P1 V1. Then this is the equation which we are looking for, P1 V1 divided by 1 minus gamma. Or since we always have started from the process 1, so we can write it like P1 V1 minus P2 V2 by gamma minus 1. This is also the same expression of this, just we have changed the sign. So work transfer in a reversible adiabatic process is given by the equation P1 V1 minus P2 V2 by gamma minus 1. The next ideal process which we are going to look is polytropic process, where polytropic process we call it as PV power n is equal to constant. Here the nature of the curve in a PV diagram depends upon the value of n. So it is not going to remain as we are showing, because it depends purely on the value of n. For example, if the value of n is equal to 0, then this total term V term is going to become 1. Then it will be a constant pressure process. Similarly, if the value of n is equal to 1, then it will be PV is equal to constant or isothermal process. Or if the value of n is equal to gamma, it becomes a reversible adiabatic process. Even though we have written a simple curve, purely it depends on the value of n. Now, the derivation is quite similar to the derivation which we had for work transfer equation in reversible adiabatic or isentropic process. What is that? For work transfer, we have equation PdV, integrate it between the limits 1 to 2, then P in terms in the place of P we want it to be in terms of V, because the integration is for dV. Then what we took is PV power n is equal to P1 V1 power n. Solve it for P, then we will have P1 V1 power n divided by V power n. Then substitute that in equation 1. What we will have is P1 V1 power n divided by V power n dV. This is constant, take it out, then this will be 1 by V power n. Then P1 V1 power n, integrate it. So in order to integrate, take it to the numerator, then V power minus n dV. Then integrate it. We know that integration of x power n is x power n plus 1 divided by n plus 1. So V power minus n plus 1 divided by minus n plus 1. Substitute the integration limit, then it becomes V2 power 1 minus n and V1 power 1 minus n. Then simplify this. While multiplying to the first term, keep this as P2 V2 power n, because P1 V1 power n is equal to P2 V2 power n. So while multiplying to first term, keep it as P2 V2 power n. While multiplying to the second term, keep it as P1 V1 power n. Solve it. V2 and V2 power 1 minus n. If you simplify this, the powers will be added. So n get cancelled out. What you will remain with is V2 power 1. Then P2 V2 minus P1 V1. W1 to 2 is given by P2 V2 minus P1 V1 divided by 1 minus n, or we can write it also like P1 V1 minus P2 V2 by n minus 1. This is the equation we need for calculating work transfer if the process is polytropic process.